Hi, today I'll be talking about a project that I've been doing with RAG, and the core ideas of my project is harnessed from this research paper, Retrieval-Augmented Generation for Knowledge-Intensive NLP Tasks, which was released on 2021 by Facebook AI Research. So before diving deep into this paper, let's talk about some common problems that large language models face today. So if you go to ChatGPT and ask a question, who is the President of America? I'm using 3.5 in my case, so you'll get a typical output like this. I can't provide real-time information. If you're looking for a current president, I would recommend checking the reliable news source. So if you go to Google and search for the same information, so you get Joe Biden and all the bunch of relevant websites that's relevant to the query. So what is wrong with the ChatGPT that it can't access real-time information, and how to trick ChatGPT to do that? The problem is, once the training stops, the language model also stops learning. And that's where the RAG framework comes into play. It's kind of tricking the model to access a real-time data. And the kind of task that I want to do is very closely relevant to what Perplexity.ai does. Perplexity uses ChatGPT on the background. So if you go to Perplexity and ask a question, who is the President of America? It goes into the internet, searches a bunch of relevant documents, and gives you an output. It not only gives an output, but also gives you a source of information. So from where it has been sourced for each line of output. So what is wrong with the ChatGPT is that it can't access real-time information. And how does Perplexity overcome this problem by utilizing ChatGPT on the background? So that's what we will be discussing today. It's RAG. So let's say we have a question, who is the president of US? First, we go and find all the relevant documents to this question. Then we kind of send it to the language model, and the language model understands the documents, understands the question, and gives you an output that's in context relevance to the question. So how do we do that? Let's take a small example. So in my case, what is RBA? So before we go there, let me show you where I'm sourcing the data from. I'm using the Hugging Face MS macro dataset, which has around 80,000 rows, which has a query, a bunch of relevant documents, and the actual answer to this. So we'll come back. So the first question is, what is RBA? And in our training situation, we already know our answer, result-based accountability. But we have tons of data. We have millions and millions of websites that might have this information. So first we want to narrow down our search. We want to choose which documents are in relevance to the question. So and here we will be using two frameworks. One is sentence transformers, a pre-trained embedding model that's available in the Hugging Face, and we'll be using the FICE, a library created by Facebook. So if you want to know deep, this website kind of provides more information why this is faster than other document retrievals. And we have something for sentence transformers as well here. And we also have an interface to play. If you give in some query and some relevant information, and irrelevant information, it kind of ranks which information is more relevant to the query and which information is not relevant to the query. So in our case, do you like pets? I like birds is more relevant answer to this question. I ate apple is the most irrelevant answer to this question. So we are using sentence piece to encode all the documents that we have, and we kind of store it in the FICE library. So once we have it in the FICE library, it looks something like this. So if you have a query, do you have pets? And you have a list of all the documents, and if you plot it in a graph, so the query, do you have pets, is more in alignment with the pets compared to the other answers that's irrelevant. So it has been pre-trained, and it has around 22 million parameters. So that's the beauty of it. So once we have that, then we kind of retrieve the top 10 documents from our search. So let's say our top 10 documents look something like this. So once we have the top 10 documents, the FICE index also gives us the scores for each document. So using the scores, we can softmax, and it kind of distributes a probability between all the documents that has been relevant. So for example, in my case, 0.12 means like 12% probability, which is the highest of all the probabilities, that this document has an answer to the given query that I'm searching for. And not only that document, the document 2 also has a relevant answer, but comparatively low, maybe like 10%. So the document 3 also has some information, but again, 10%. So we want our model to fetch information from all these websites and give us a compiled answer. So how do we do that? Let's see. So once we have the top 10 documents, then we kind of concatenate each document to the query and we kind of pair it with the answers. So that's what's happening here. So we have 10 retrieved documents. So each query is concatenated to a document and we have an answer to that document. So basically the same query, the same answer, but a document 2. Same query, same answer with a different document. So we have 10 pair of these documents and the answers. So once we have the 10 pair of these documents and answers, we kind of send it to the encoder decoder model. So in my case, I'm using Google T5, so which has around 223 million parameters. So once it goes through this model, it kind of gives me an output, which is the loss, and it also gives me the logits and all the gradients. So in my case, I won't be interested in the loss that the model gives because the loss is an average of all this one. Sorry, it's not an average of all this one. So it's a cumulative loss. I'm not interested in this one. So I'm kind of only taking the logits at the moment and I'm kind of soft maxing it. So once I have the soft max, I multiply it with the actual soft max probability distribution of the top 10 documents. And then that gives me a unified output. So which goes into my custom loss, cross entropy loss, and that gives me an output. And I backpropagate all the way to tune these weights to make the model learn. For this query, you need to give this answer, and somehow you need to adjust your parameters accordingly. I won't be adjusting all the parameters. So in my case, we have around 223 million parameters. I'll be using some techniques like PEFT, parametric efficient fine-tuning, and very specifically, I'll be using low rank adaptation techniques. So to reduce the computational cost of it. So I will show you in the code how it is happening. Yeah, that's pretty much it all. So once you have the cross entropy custom loss, then I backpropagate all the way to tune these parameters and weights. So let's see what's happening in the code. So I have all the basic libraries imported in the beginning, and then I'm ensuring if my model is running on the GPU. In my case, I'm using A6000s, and I'm kind of downloading the tokenizers, models, and sentence transformers. And straight away, I go for LoRa configuration. So my target here is queries and the values, and the dropout ratio is 5%, and the task type is sequence to sequence. I want to give a query, and I'm expecting a query as an output, and I'm expecting a sequence as an output. So I kind of send my T5 model with the LoRa configuration to gift PEFT model. So that would be the model that I will be using for this one. And if you see, there are around 224 million parameters. So the initial model has around 223 millions only, but we have more than 1 million parameters added here. And that is because of the LoRa. We have around 1.76 million parameters added, and which is only trainable. So less than 1% is trainable. The rest of the weights are frozen here. And the data preprocessing, I'm not going to talk much about here. So it's basically, I'm getting the query answers and the passages from my document. Now I'm kind of taking all the unique documents from the passages and I'm batching it. And it kind of took me 5 or 6 hours to do this whole batching thing. So I kind of saved the output for quicker rerun. So, and I'm kind of loading it and putting it into the download loader. And yeah, so here I'm using like really a small data set, just 50. Again, for visualizing the results, it becomes really easy if you have a smaller data set. And here I'm setting up the model. I'm sending it the LoRa model, and it accepts encoder inputs and padding mask for the encoder and decoder inputs. And I'm not setting any padding mask for the decoder because all my outputs are of same length. So it's pretty much unnecessary. And the causal mask is kind of handled internally by the model itself. So no need to worry about that as well. And setting the optimizers and saving it in a place for every output. And this is the architecture of my model. Yep, so in the training part, I'm kind of wrapping up everything under TQDM. And when the input goes, it kind of gets tokenized. So the tokenizer, T5 tokenizer gives me 2 outputs. One is input ID, one is attention mask. So this goes as an input for my encoder. And for the decoder, I'm sending in the answers. And I'm only considering about the input IDs. I don't worry about the attention mask for the decoder because it's unnecessary because all my answers have the same length, unlike my inputs. So I'm kind of shifting one token right for the decoder input and the label one token left, which is a normal practice. And I'm sending it to the model here with all the inputs that I've created. So, and it's storing it in the outputs. I'm not interested in the loss, so I'm just only taking the outputs.logits, and I'm kind of applying softmax for the last dimension. So the softmax to logits is again multiplied with the score, which is the actual probability distribution between the top 10 documents, and finally summed up on the first dimension. And I'm sending it to a custom loss function here, cross entropy, with the predictions and the labels that has been flattened. And I'm doing the backward and the optimizer step to backpropagate. And yeah, I'm saving the model for every pool. And the loss was kind of pretty good. It was recently ready using. Was quite happy about it. And in the inference part, I'm again loading the model, setting up the class and the model that I have been saved, and pre-processing the query with a bunch of starting tokens and the ending token, and it's ready to go into the model. Yep, so I kind of visualized what's happening inside the model for each step. So my input IDs are of shape 10 by 158. So I have 10 relevant documents, and the maximum length is 158, and the attention mask is of the same shape, which is pretty good. And for the decoder, I'm sending in 10 by 5 with the padded tokens, one token shifted, and the labels look something like this. So the output is in the fashion of 10 by 4 by 32128. So the 32128 is the vocabulary size of the model. And I kind of softmaxed it. The softmaxed shape remained the same. I wanted to ensure if I did the softmax on the right dimension, so it's equivalent to 1, close to 1, I'm pretty much happy. And I'm multiplying the softmax, the shape remained the same here. And after summing it up, the shape went from 10 to 1 here, which is pretty much expected, and it's going good. And to ensure if I have did the softmax on the right dimension, I'm kind of summing up the first row to see it. And the output comes out, and I'm kind of decoding it and predicting what it has predicted. So in my case, it's pretty bad because I was training on a very limited amount of data just with the intention to visualize what's happening inside. And also I did a small mistake, if I have to be honest. I used T5 model, which is basically designed for language translation purpose. So if you see, translating English to French and hello, how are you? And it kind of translates it. So this model is not originally trained for question answer, but initially it was trained for language translation. So I think it translates for 5 languages, but it's pretty much not useful to my purpose. But this is the whole outlook of how we do the RAG. And the best part is we take the softmax of the top 10 document, then we multiply it with the logits. So that's the best part, which most of the methods will ignore. It will pretty much take the information from the first document. In my case, it's slightly different, and it has enriched output compared to the other normal models. So yeah, I have also added a link to the code in the GitHub, so feel free to give a check if you're interested further.